Bismillah ar-Rahman ar-Rahim. Welcome back to our course, Deep Learning for Computer Vision. Today we are dealing with lecture number 20, and it will be regarding the convolutional neural networks, and we'll dive a little bit deep into the definition of the CNN, its components, algorithms that can be used in order to obtain our deep learning neural network. Let's go and see what about this topic and how we can see the benefits of having such networks. As you see from the title here, CNN's algorithms and components. Now, this lecture's guidelines are as follows. Introduction to CNNs. We'll talk about CNNs and the historical background. And next, we'll try to have a deep and a closer look on CNN components and what are the main components of the CNN and how we can connect these CNN components and to make them interact and to give us the result that we are trying to get. And meanwhile, through the lecture, there will be some demos on CNNs. We'll start with some history background. In fact, since 1950s, there was a try to deal with AI research and struggle to make some systems that can understand the visual data. The success was very little bit, we can say, very poor, and it was a long time before getting the new achievements in the last few years, maybe in the last maybe 1 or 2 decades. However, the work regarding the image processing applications that are oriented toward computer vision and making AI systems has got a name as computer vision, and this was what we started our course with at the beginning of this course introduction information about the CD or computer vision applications. It was a long time before getting between 1950s and 2012. There was the first work which was as a very, very big push to the deep learning, let's say, research direction. And this was a quantum leap when a group of researchers, led by Alex author, and they call or they named this network as AlexNet, and they developed an AI model that surpassed the best image recognition algorithms. This model was able to classify images into classes, and it outstand in its performance other classical image recognition algorithms by a good margin. I won't say about a large margin, because it was a starting step in this direction of research work and in the field of deep learning. It achieved about an increase of about 85% when compared to the runner-up, scored a modest 74% on the test, about 10% improvement. And this was the opening of the deep learning era using CNNs at that time. It was about 22 years ago. Sorry. So at the heart of the AlexNet, the main topic here, the main idea behind all these things is that AlexNet implemented the convolutional neural networks as main block, the main block of building the deep neural networks or deep learning systems. If we start to talk about the AlexNet, it contains 8 layers. Let's have a look on the block diagram of this deep learning network. Here, the photo of the author Alex. It contains, as you see here, we have 8 layers. 8 layers. okay, with learnables. Let's correct this. So it has 8 layers with learnable parameters. This means that some layers are not learning or doesn't have the some layers doesn't have learnable parameters. Or for example, the ReLU or the activation function, you apply the input and you get the output. There is nothing to learn from that. There is no modification on the learning parameters in this system. The model consists of 5 layers with a combination of max. So we have 5 condition layers uh, with max pooling layers. Here, as you see here, we have these condition layers, okay, and they are followed by max pooling layers. Here, we apply convolution and max pooling with ReLU activation function. These layers, except for the output, we have here fully connected layers, 1, 2, and finally we have a softmax layer with 1,000 different classes for classification purposes and for pattern recognition or image recognition applications. So if you look at the block diagram of the system, simply we can start. Let's zoom this one a little bit. Okay. So this is the input image, RGB image with the size of 227 by 227 by 3. It's an RGB image. Here we are going to use this one. Here we are going to use different CNNs, convolutional neural networks. As you see from the first part here, we can see that this is a convolution application or convolution layer with a kernel size of 11 by 11. Next, this will be followed by another layer, and every time we have convolution layer CNN, it's a CNN connection, it's a convolution layer, conv layer, followed by pooling layer, and sometimes or every time we have a ReLU activation function. We'll talk about this later in details. At the latest stages, here we have, as you see here, we have 2 fully connected layers. We talk about this in details. And these 2 layers are followed by a softmax layer with 1,000 classes at the outputs. So what is a CNN? Or we call it sometimes convolute. What is convolute? This slide, I think, it is repeated somehow from other previous lectures. However, we'll try just to recap the information there. CNN is a specialized type of deep learning. So it's a very specific type of deep learning that opened the doors for big results and explored high performance applications, mainly designed for tasks like object recognition. So the convolutional neural networks CNN are designed mainly for image processing applications and for to tackle or to deal with images with let's say with goals or objectives to have at the output object detection, localization, segmentation, classification. All these topics can be obtained and these tasks can be obtained using the CNN networks. They are very good at picking on patterns in the input image. So using CNNs, you can, let's say, select or pick up the features in the images and concentrate on the features map, let's say, instead of the image itself. This includes lines, gradients, circles, even eyes, maybe faces, maybe parts of objects, maybe body actions. All these things can be captured by the different CNNs. You can find CNN applications everywhere almost, actually in practical scenarios, for example, for autonomous vehicles. So when you have a driverless car, for security camera systems to give Uh, for example, in mobiles, when you try uh, open your mobile and get in, you may spot a system, or it's always there for sure, with a face recognition software that identifies your face and whether it is you or not. And this can be done using CNNs. The list is very long, and we cannot here mention all these applications. However, CNN again, CNN approach was very strong enough to open a wide and a tremendous variety of applications for deep learning in its field. What is the main idea or the inspiration behind the CNN? Of course, if you look at CNNs, they are inspired by the layered architecture of the human visual cortex. As here, when you look at we need some here some uh, details from the brain structure of dealing with images. Suppose that this is the eye, here the retina. It captures here the image will be captured by the retina, sent by the neural nerve to the brain. In the brain, we can now uh, see how the processing is done there by the visual cortex. As you see here, we have the retina, and we start here the interaction between all these parts of the brain to perform a specific or a given operation, uh, to define or to describe or to classify this animal, let's say, or this object in front of the eye. Now, mainly, you look at the input image here. It is similar to be having some convolutional layers, convolutional operations, followed by pooling to reduce the temporal information and increase the feature domain parameters. And step by step, by going from V1 to V2, then to V3, then to the last part, which is the IT part, the visual cortex. Uh, every time you go further in reducing the temporal size, or the, let's say, the spatial size, and increasing the feature map size. And finally, using the interaction between the brain parts by having the information from V1, V2, and V4 receptor fields, you will get an output, and this will give you an ability to recognize that this is a dog, not a cat, for example, or maybe not another animal also. So this is the main idea behind how the CNN are built to mimic the human visual cortex in the brain. Clearly, that the CNN in general extracts basically from the beginning structures like horizontal and diagonal edges. So we start by edges. This will be at the first stages, the early stages in V1. This can be done somewhere at these places, V1. Next, you will go further by increasing the feature maps domain, the details, and reducing the spatial size. This will detect more complex features such as corners, uh, combinational edges, maybe curvy edges, maybe triangular shapes, maybe other things like in this issue. And when you go further and further, you can even identify more complex features like subjects like objects, like the head of the dog, maybe the small ball in the dog's mouth, and sometimes we can go to deeper and deeper to get some information about the faces and recognize different types or different faces, different objects within the image. This is the main topic or the main idea behind using the CNN in general, and this is let's say inspired by the human vision system and the human virtual cortex that is interacting in brain to provide or to perform classification and segment say recognition purposes and applications. Let's go now and go to have a deeper to get a closer view about the CNN itself. So, what are the key components in CNN? Mainly, we have four main components. The first one is the convolution layers, the very important part that mimics the human brain visual cortex. Next, we may have in CNNs the pooling layers that converts, let's say, the spatial information or reduces the size of the spatial information, the size of the image, and increases the number of layers, number of, let's say, feature map size. Then the rectified linear unit, which is a very simple activation function, it will be helpful in reducing the size and speeding up the process of getting the final getting forward the final steps. And finally, the fully connected layers that are used to convert the inputs into numbers in terms of the probabilities for classification purposes using the softmax layers. We'll talk about all these components in details next. This is an example on using, let's say, CNN for recognizing written digits into specific digits. Like, for example, here have an input of an image having, let's zoom this a little bit. So we have here an input image, as you see here, of the handwritten digit 2, and this is of the size 28 by 28 by 1. Now we'll use a convolution layer, first layer, with a kernel size of 5 by 5, and we'll talk about these things in details. Then followed by max pooling by a factor of 2 by 2 to reduce the size of the image. As you see here, we have the size here is lower than, it's about half of the input size to the max pooling layer. Then another convolution layer, another max pooling layer, etc. All these steps will be repeated until we achieve a condensed, let's say, a feature map. Next, we go and apply, as see here, flattening, so converting this 4 by 4 by n2, let's say, a vector or tensor, and we try to flatten it and apply to the fully connected layer. We have more than one fully connected layer. This will replace the inputs terms or samples in the vector by their probability values, and according to the received probability values for the digits from 0 to 9, we, for example, find by softmax layer what is the max probability. Let's say for in this case we get a value of 0.85, for example, and this will give us other probability, of course, for all these digits will sum to 1, and this means that maybe it will be like some value like 0.85 will be the highest value, and this will give you segmentation, or let's say that this class or this handwritten digit is 2, as you see by the received or achieved value of the probability at the softmax layer at the output. Usually we use softmax at the output layers. This is a small demo. Of course, we'll talk about these details and things deeper, and it will be very clear for you. So don't worry, and try to follow the description in this course, in this lecture for sure. So the convolution layer, what it stands for? It serves as the fundamental building block. So the CNNs are based on convolution layers, where we apply the convolution application or the convolution operation on the input image, and it takes most of the majority of the computation regarding the deep learning neural network in this situation. So in CNNs, the convolution preserves the spatial relationship, so it actually preserves the relationship between the pixels in the spatial domain, in the time domain. I mean, in 2 dimensions, in the x and in the row direction and the column direction, while it learns features about the image starting by edges, then going further to more complex, let's say, features like uh, uh, circles, dots, uh, small window sizes, and we usually apply the convolution layer, as you know from previous lectures, that by applying by convolving, applying dot production between a small window, we call it or matrix, we call it the kernel, and by moving this window all over the image pixel by pixel to get a new output, or having usually the same size as the input, but with concentrating or with getting output related to the features in this, let's say, image, or to a matrix. It could be one layered image, for example, grayscale, or it could be colored image. So simply, if you look at this image, here we have the input image of the size 32 by 32. This is the input handwritten image. And let's say this is the presentation of the pixel uh, in case of a matrix shape. Of course, the number 0.1 and 0.2 is a scale version between 0 and 1 of the grayscale value adopted by this format. Now, if we apply the convolution, for example, in this case, you may apply the convolution between these values of the digit 2 with the kernel matrix, as here we have zeros diagonally and ones also diagonally. If you look at this, you can see simply that what is going to be here we have almost the shape of maybe the digit 2, something like this way, and it could be a little bit wider, okay, and we can apply convolution with this part of the matrix. Of course, this is not the full image of 2. It's here we have a part of this. We may see this as a part, maybe this one, a part of the image itself. So we have very similar here. And we just need to apply the dot product with a kernel matrix. Here we call this as a kernel matrix or convoluted matrix, but this is the output, of course. Here we have the result of applying of course, this topic has been explained in details. We just want to recap and to understand that this is done usually by CNN. And here the most important thing is how we can use these kernel matrices, and we call it in the field of CNN as a filter. Usually we apply the convolution operation to the input with a large number of filters, maybe 16 filters, maybe 8 filters, maybe 64 filters, more or less, depends on your application. And the more filters you use, the higher the extracted features from this input image. And with the help of max pooling or pooling applications, you reduce the spatial domain and increase the features domain. Okay. So in general, CNN is based on the convolution layer, and we use usually a lot of convolution layers with a lot of number of filters that are usually followed by either max pooling or maybe other types of components in the CNN. We'll see this a few minutes later. Now, again, what are the parameters that control or that governs the convolution layer itself? Let's see. This one is the kernel size of the matrix or the filter. So in this case, we usually use small kernel matrices. In this, we denote it as K. Usually we take a value of 1, 3, 5, 7. It could be also higher or bigger size, but this is the commonly used sizes for the kernel size. A new term is called the stride. What is the stride? The term is the step. So when you apply the convolution, we usually in image processing and computer vision, we apply a stride of one, which means that you just, after finishing the dot product between the kernel matrix and the image, you just move the kernel matrix by one pixel to the right, and by finishing the first row, you go to the next row, and so forth. So the stride here means the step that you are going to make between the convolution operations during your working on the image. So the number of pixels that the kernel will move during this operation is called as a stride. We usually use a stride of 2, 1, maybe 3, but not very common. We use the stride of 3 unless we have a specific or specific neural network or commission neural network case or situation. The padding, of course, we know what is the padding. Sometimes when you are working at the upper left corner or the bottom right corner, when you try to access the first row, the last row, the first column, the last column of an image or a matrix, you will be having some pixels in the kernel outside the image. And in order to make this operation okay, you do the following before starting. You just need to add zeros in surrounding as a frame surrounding the image in order to make the operation smooth and straightforward without any problem. So this is the padding. I think you know what's the padding from before. So you can now go back to your lectures, maybe lecture 4 or 5, where we discussed the issue of padding. Now the number of filters or depth of the system, the CNN system. Here, the number of filters means the number of kernels that are going to be used sequentially with the image to obtain the features or the patterns in this image. This can be done, of course, it may vary between, let's say, 2, 4, 8. You can select more or less according to your application and according to the number of patterns or features that you are trying to extract from this image. Now, after applying convolution to an image, let's say of the size n by n, we want to find out what is the size at the output. So if you have an input n by n, what will be the size of the output? Simply, this equation will help you to define the size of the convolution layer output. So the output will be equal to in. This is the size of the input. Let's say n by n. So we take n for example. Next, minus k. Minus k, what is k? The kernel size. Plus 2p. What is p? Is the padding, 2 multiplied by p, divided by the stride s, okay? This will define for you the size of the output, So if you have, for example, the size of the input, you have the size of the input, for example, we have, let's say, try to take this from here. The input size is m. You want to find the output size m dash, and the input size is n. I want to find the output n size m. Now m dash will be equal to the input size m minus k plus 2p over s plus 1. Suppose that you have m equals, let's say, 32, k 3 by 3, p padding, let's say we have a 0 padding with, let's say, with no padding, so we have 0, and let's take a slide of 1. What will be the output m dash or m prime? So we have 32 minus 3 plus 0 over 1 equals, okay, plus 1 here. So let's correct this somehow. Okay, plus 1. So this means that the output value will be 32 minus 3 it will be 90, it will be 29, plus 1 it will be 30. This is for m. If you want to find n, you just need to repeat with n dash, you just need to repeat with the value of n and the kernel size in the vertical direction with the padding, etc. We usually use the same kernel size, square kernel sizes. The stride is for both cases the same, and for the padding is the same thing is true. And here we have a good example about p equals 0, there's no padding, and s equals 1 with a stride. As you see here, when we look at the pixel at the upper left corner, for example, let's take the first pixel, this one. You see that the output here, or the let's say the kernel matrix, will be obtained from, or the output will be obtained from a matrix of 3 by 3, because we have zero padding. There is no extra zeros surrounding the image, and the stride will be clear now if we pass to the next step, as see here now. So if you look at this situation, we moved by 1 pixel to the right because we have a stride of 1, and we repeat this process until we finish all. We get to the end of file or the end of the matrix or the image layer at this location. Let's take another example. Here we have zero padding, and see that these dotted lines gives you an information about that. We have a zero padding p equals 1. Zero padding p equals 1. Let's have another pen because the color is not very senior. So p equals 1. And the stride again, if you look at the stride, we are moving every time by 1 pixel to the right, 1 pixel down, and this means that s equals 1. So these are different examples on the meaning of the stride and the padding. Here we have a stride of 2. This is a good example here. So if you look here, let's start from here. Okay, if you take this example here, we are at the upper left corner. Now, if we move next, as see here, we have left or made shift of 2 pixels here. So we have shifted to the right by 2 pixels. This means that the stride has been selected to be 2. Of course, in this case, the size of the image will be, or the output will be reduced by a factor of more or less by a factor of s, and this will give us an ability, of course, to reduce the size and increase the feature map size. But of course, if you have to be careful, because when you take high s values, or maybe s equals 2 or 3, this will a little bit damage or reduce the let's say unlearned relationships between the pixels in the spatial domain, and this must be taken into account. Here we have a padding of 1 and a stride of 2. The same thing is true, but with adding a frame of zeros around the let's say image layer, or the input matrix in this case, because not always we have an input and image, because at the intermediate stages of the convolutional neural network, you will get some convolution operations where you get at the input a feature map, and the output is also a feature map. So in this case, you have to be careful with these parameters. We learned the convolution that it was linear convolution. There is another type of convolution also that you may face. In fact, very rarely, but you can see this. It's called the depthwise convolution. This type of convolution is performed on each image channel independently. So you apply the convolution layer to each channel independently. So at the beginning, you take the input image, let's say the f by the f, with a number of channel equals m. In this case, for example, if you have an RGB image, you will deal with 3 layers, m equals 3 in this case. Now you try to get the output of the depthwise coding or convolution, dp instead of df, and this can be obtained by splitting every channel and applying the convolution to every layer, single layer, and let's say independently. So there is no channel information to be transferred. We only take every layer of the channels without assuming or considering the other layers in our calculations. This is called depthwise convolution. So the convolution is done in a depthwise approach, and this is why we call it depthwise convolution. Also, you may face something which is called pointwise convolution, or the one by one convolution. You may be wondering what is the main purpose of having one by one, how to apply one by one convolution, what is the main concept behind the one by one convolution. In fact, the main idea behind the pointwise convolution, which means one by one convolution, is to reduce the size or to match the size of the input and the output layer. Sometimes in some systems or some classification problems, maybe you may get some mismatch between different parts of the system, and in this case we try to change or match these let's say layers by applying the pointwise convolution. So what is the pointwise convolution? It's a convolution type that can be used to change the dimensionality, number of channels of the input. So you have, for example, at the input you have an image size of 32 by 32, and the number of channels is, let's say, 16. Where the next step you have at the output, you have a number of channels 32. So you can use one by one convolution to keep the spatial size as is, or in the two-dimensional size as is, but by adding more filters to get the 16 layers to be becoming 32 layers. So this is the main idea behind using the one by one convolution. Also, it can be useful to create channel-wise dependencies with a negligible cost. It looks like it helps you to reduce the calculation, the size of the calculations. As here we have the image of this size dp by m channels. Okay, it's a cube. What is going to be done in the pointwise convolution? We are going to take one by one pixel with the dimension or the number of filters m, and get these components this way. And this will give us the size of the image itself. Let's say we have to define the number of filters, in this case as n. And finally, after applying this will give us, so you started by a number of filter m, and you finished by a number of filters that is, let's say, for example, you have here 16, and here we want to reduce or to increase maybe to 32. You can just do this by changing the number of filters. So when you apply one by one convolution, the input may be, let's say, 32 by 32 by 16, while the output may be, as a result of applying the one by one convolution, 32 by 32 by, if you select here n equals 32. This can be done for adaptation purposes, and it's not a very heavy operation on the computers, and doesn't, let's say, seriously modify the network and its performance very strongly. Okay, what else? Let's clean this. This is regarding the convolutional layer. Also, in the last few years, new types of convolution are also available, like the separable convolution. The main idea here is to, let's say, try to reduce. As you know, when we deal with, let's say, a 3 by 3 convolution, it's not very difficult to know to see that it requires some calculations. Now, when increasing the number by the kernel size by 5 by 5, 11 by 11, etc., in this case, the calculations will be repeated very heavily and will overload our computational cost very seriously. So instead of having a kernel, let's say 3 by 3, you can divide the kernel into separable conversion steps as 1 by 1. Okay, so we can take the conversion as 3 by 1, then repeat for the result for 1 by 3. So this matrix can be obtained, for example, by converting the input image by the kernel matrix 3 by 1, 3, 4, 5, and the result will be applied to the other step, which is 1, 2, 3. This reminds us with the kernel matrices that were used in the discrete cosine transform and in the Fourier transforms by applying the separable matrices or the composition matrices or vectors to separate or to apply the let's say the convolution operation in regard to the channel to the let's say the pixels in the rows, then apply transpose to the rows of the of course for the output, and repeat the same process in order to use the same matrix or the same vector with in the row direction and in the let's say in the column direction. This improves and increases the speeds up the system and gives you a quick approach. However, sometimes it may have some limits and it may lead to some distortion in the output of applying such a separable conversion. So you can replace the classical conversion by a separable conversion, but you have to be careful because sometimes this may lead to some distortions. You can check whether for 1, 2 stages and be careful with these. We'll see this, inshallah, in next lectures when we talk about the let's say examples on famous and well-known deep neural networks based on CNNs. Also, we have something which is called transposed or deconvolution or inverse convolution. The main objective of this layer or of this technique is to invert the operation of the conversion operation. So it looks like a sort of upsampling. So when you have convolution, you get features, and you may use the transpose convolution in order to reduce, to increase the size of the image by working. Of course, when you have a convolution layer 3 by 3 with a specific number of filters, but we have, with, let's say, for the stride of 2, and the size, for example, 32 by 32, you may get an output reduced to 16 by 16. Now, when you apply transpose convolution to the 16 by 16, applying a stride of 2, this will give you 32 by 32 output matrix. So the operation of the transpose, you just need to think about it this way. It's a sort of opposite operation to the convolution in terms of the size of the output to be upsampled instead of downsampled after applying convolution specifically when having a stride more than 1. Here you see, this is the transpose convolution. So here, if you look at the case here, actually, this is the input, and this is the output. So it's opposite. It was in the previous slides something like different. So when here we have zero padding for sure surrounding in order to get the proper size. Now, as here we have as padding of 1, but the input size was 2 by 2 and the output size is 4 by 4. So it will give you a sort of upsampling of the input. So this can be done when you want to go back from the let's say the feature domain to be closer or to go further to get the spatial domain representation. Another type of convolution is called the dilated convolution. Here, the pixels of the kernel are spaced with zeros in between. This increase of the filter size will not damage or affect seriously your operation, but it will also not increase seriously the competition. Let's have a look on this technique. You see here we have the size 3 by 3. It becomes, for example, in this case, if you look at this image, the size was actually the blue pixels are 3 by 3, and this is the output size, which is now instead of 3 by 3, we get here 1, 2, 3, 4, 5 by 5. So this is the main purpose of using the dilated convolution. It works like the transpose convolution. However, by just without zero padding, or you can use zero padding, but the main idea is that we added zeros in between the pixels in order to not increase the competition and not seriously affect the performance or the quality of the output, let's say, transposed or dilated layer after this convolution application. Let's go now to the pooling layers. In the pooling layers, the main topic or the main idea behind the pooling is to reduce the size of the output, usually feature map. Usually in CNNs, you will find that the convolution layers are stacked layer by layer with the pooling layer, one after the other. So you get a convolution layer followed by a pooling layer, and sometimes maybe followed by other layers like ReLU or activation functions. Okay. Usually we use the pooling layers to reduce the size or the dimension. And this will help us to get a compact feature map instead of the expanded or the large-sized, let's say, spatial or temporal input layer. This gives us an ability to reduce the number of parameters to learn and the amount of computation that will be performed in the network. So you can now look at the pooling as a compactness or a compacting operation that leads to reduce the size of the parameters. This will be helpful in learning the information from lower number of parameters and will reduce also as well the computational cost that will be performed by the network. And this is very well working actually in all CNNs in all aspects. Again, we repeat the same idea that we are going to perform the our operation on the next stage on a summarized version of the features instead of the precisely positioned features generated by the convolution layer. So instead of taking the exact locations or the features generated by the convolution layer, we are going to replace this by a summarized features version to make the learning easier and quicker. What are the types of pooling? The first type is the max pooling. This type of pooling is used usually at the early stages of the system, maybe in the intermediate stages also. It just selects the maximum from a group of elements of the feature map covered by the pooling or the max pooling filter. If you take max pooling, so you are concentrating on the maximum values or the features having the max values. So this will give you an ability to focus on the prominent features of the previous feature map, and in order to continue processing and learning from these feature maps. Let's have a look on this image. Here we have the input. Let's say in 2 dimensions, x and y. I'm going to use a max pooling with a stride of 1. So the size of the pooling layer is 2 by 2. So we take 2 by 2 window. And we look for, as here, and we want to find out the output for all. So in this case, if we take this part, the max will be 237, and this location. Now let's remove all this. We by taking a stride of 1, we move to this location by 1 step to the right. Again, 200 37 will be obtained. We next move by one level to the right, one pixel or stride to the right. This will give us 232, and so forth. We repeat the process. Now, if we take a stride of 2, this means that we'll take this part firstly, then we shift to the right by 2, shift down by 2, and shift down by 2. This will give us, suppose that this is the size, as you see here, we have 4 by 4. In this case, we will get the output with a size of 2 by 2. As a result, when you want to seriously reduce the size, you just need to increase the stride number, and sometimes this will affect your image either positively or your system either positively or negatively, and it's a matter of experimental and empirical calculations and testing of your designed system. Here another example, as here, we have the output here somewhere. Just a minute. Let's repeat again. I see that the numbers in red are the max values. Here we have a stride of 2, because we are shifting every time 2 pixels, and the size will be reduced with the prominent feature points and values in the output achieved by after max pooling. We can find also average pooling. Instead of having max, we use the average operation instead of the maximizing or taking the max value under the filter. So the average pooling tries to find the average in a patch in a specific in this input. As you see here, we have a stride of 2 again to simplify our calculations. As you see here, we have 1, 3, 4, 6 for the first run. And you combine 3 plus 1 plus 4 plus, you just need to combine plus 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 and find the average, and this will give us a value of 3.5 or 7 over 2. We repeat this process with a stride of 2, so we shift 6914. This will give us an average value 15 plus 5, 20 over 4. This will give us 5, etc. We continue until we finish our operation. This is an animation example on average pooling. You can see here we have a stride of 2 again. When you move, you can see the action of finding the average value in pooling operation. What are other types of pooling? We have global pooling. You use to sample or to downsample the entire feature map into a single value. So you globally average, not average, globally apply pooling. It could be max pooling or average pooling. And in this case, you apply, you get at the output only one value instead of having a matrix at the input. This means that you are setting the pool size to the size of the input feature map. So the size of the kernel matrix or the patch will be equal to the size of the input feature map. In fact, this can be done or obtained usually. It was used earlier with an objective to replace the fully connected layers that will be discussed later, and we already talked about the fully connected layers because the performance in this case, global pooling is much faster, but in fact, the performance in case of using fully connected layers is higher. However, what we can do here, as you see from this image, now we are going to do the following. We take, let's say, the height and width 6 by 6, and we have replaced all values in the global pooling by one value. Of course, here you can use max pooling, can use average pooling, depends on your target that you are going to do. And for the second layer, we used also the average pooling. And so we get, instead of all the input feature map, three-dimensional matrix, we just obtain three values. Every layer has only one value as the output. Also, this something we call this stochastic pooling. Here we randomly picks this type, randomly picks an activation within the pooling region based on a multi-nomial distribution formed by the activations in that region. What does that mean? Let's have a look on this image here on the right corner, bottom corner. This is the input. Let's say this is the input of our activation or operation before applying the pooling. We, due to some probabilistic or stochastic operation we performed on this output of 3 by 3 matrix or feature map, we obtain these values. Now, according to a specific rule, we may select a specific value of probability. For example, let's say maybe in this case we have selected the value of 0.13 to get the pixel or the value that we are concerned with, or the feature map value feature in this 3 by 3 window. So what I'm trying to say that you are using stochastic rules in order to pick a specific feature value within a kernel matrix or a batch size, window size, in order to define which feature map is very important for you in this case. As an example, here we may take this value, according to which we can pick the feature map at the center with having a value of 55, and this is the output in this situation. These two types are very rarely used. However, you may find, and in some systems, maybe in research applications, you may find some of these pooling types. So I just included these types just for your info and for your convenience. Let's go back to the fully connected or the dense layers. Either we can call it fully connected layer or dense layer. Now, the fully connected layer, it's a layer where you can find it in almost most of the convolutional neural networks. It was proven that it has a very successful results in recognizing and classifying images for computer vision applications, and it has been intensively included and implemented in CNN-based deep learning networks. Now, in fully connected layers, usually, what we mean by fully connected layer, as here, if you look, let's zoom this image. If you look at the inputs, usually we use this at the final stages of the deep neural network. These inputs are maybe obtained by flattening the input matrix or the feature map to dimensional into one dimension, and every single component here is connected to all. As here, the output is connected to all inputs. So we call it as a fully connected layer because every output is connected to all input layer values or input map, feature map elements, and this is why we call it as a fully connected layer. Why we use this? Usually, when you apply fully connected layer, the main purpose is to prepare your data for the output. And this can be done by converting the input values of the feature values or the feature components to class probabilities. So in this case, A, B, C, and D are classes with probabilities according to the inputs from A to 9. And when A is calculated, it has been calculated using all the inputs at this fully connected layer. This will give you an ability to recognize or to classify the input at the start of this deep neural network into a specific class, either A, B, C, or D. I mean in this example. As I have just mentioned that they are usually placed at the end of the network, and you can use one or two layers prior to applying the softmax classifier. So they are usually accompanied with the softmax classifier. As you look, as you see here in this, you look at this image of this network. Here we have the convolution plus ReLU plus pooling repeated many times. After a while, you get to flatten. This means that to convert from, let's say, to dimension in one dimension, then you can use fully connected layer, one, maybe two, maybe three. And finally, at the output, if you look here, all these things here. Okay. If you look here at the output, these are the classes. And from these classes, we can define now the type of the, let's say, animal. We have horse, zebra, etc. And the operation will be based on using softmax activation function that we already discussed this part in previous lectures. So this is the main idea behind using, specifically in classification tasks in neural networks and deep CNN networks. And they are actually working very well and performing high and good performance for accuracy and other parameters. However, the fully connected layers are computationally costly, and it would be let's say advised not to use more than two or three fully connected layers in your system or in your design. What are other layers? You may face some layers like dropout layer. Dropout, from its name, here you may get in your system a sort of drop. As you see here, if you look at the usually used layers, you may start by having these input neural neurons, and maybe we start from here, from below. This is the input layer. Now, instead of connecting all input layers to the all neurons in the hidden layer, you may apply drop, remove, or disconnect, or unconsider these neurons for some inputs, and this will lead to what we call it the dropout. Dropout is usually represented by a percentage. For example, 10% dropout, 50% dropout. This means that in 50% that 50% of the neurons are not connected to the inputs, and in this case, this will be helpful in actually, and of course, this dropout or these connections are selected randomly. We just use by nullifying their out, so we just put their weights W equals to 0. And in this situation, we increase or speed up the process and try to avoid the overfitting. What is the meaning of the overfitting? That you have a data set that is, your system is working very well on your data set, but when you apply your input from a testing data set, the output will not be performing the same good, to be as good as it was during the training stage. And this is what we call the overfitting. One of the solutions to avoid overfitting is the random use of dropout. In this case, we have a layer called the dropout layer that is used to regularize or to improve the regularization application by dropping out or by removing or by nullifying some of the neurons in the system. Now, we have sometimes to apply batch normalization layer. Now, the batch normalization is a technique that can be used to normalize the activations of a layer. So instead of having a wide range from plus to minus infinity maybe, or from min to max, we just need to set this within a range between 0 and 1. This will unify or will make it possible for us to dealing in an easier way with the, let's say, the the activation values or that are passed to the next stage. If you have a look on to understand this topic, here let's have the input as see here. Okay, here we have an input. Here we have the features. Suppose that this is the first sample, second sample. We have a batch of 3 samples. Okay, and we want to find the batch normalization or the normalization step. Now we first find the mean. So the mean for all these samples is just a minute. The mean will be 1 plus 3 plus 8 divided by 3. Next, we repeat for this one, and etc. We get the value of the mean. Next, we find the standard deviation. You know how to calculate the standard deviation. And finally, find the batch normalization of the input x or for this batch. It will be the x value minus the mean divided by the standard deviation. So x minus mean divided by standard deviation sigma, let's say. So in this case, this will make our system be within the range 0 and 1. It's a sort of a type of regularization approach is taken to improve the performance of our network and to avoid open intervals for the inputs to be applied. Let's have a look on the one of the examples, the first examples of the CNNs, the LeoNet 5. It was published in 1998. The paper was called Gradient-Based Learning Applied to Document Recognition in the IEEE Proceedings of IEEE by Lusan and a list of authors. Let's see what is the main idea behind this example or this simple network. It is used for digit recognition and classification. So, and it accepts images of the size. Let's increase this in size a little bit here. So the input is of the size. It's an image, grayscale image of 32 by 32. See here. And then we apply 5 by 5 convolution operation with a stride of 1. We get 28 by 28, etc. Let's go step by step and understand what's going on in this system. So here we have a convolution operation, k equals 5, stride of 1, pulling 0, and the number of filters is equal to 6. So the output will be, according to this equation, is n input size is 32 minus k, which is 5, multiplied by 2 by 0 over stride of 1, which is 1, plus 1. This will give us 28 by 28. And the number of filters, be careful with this. The number of filters is defined from the beginning to be 6. So the size will be 28 by 28 by 6 layers. Next, we go to the next layer. Here we have to use average pooling, the size as given by the description of the paper, k equals 2, and the stride of 2 with a number of filters equals 16. If you go now to find the output, it will be 28 by minus 2 by 2 by 0 over 2 plus 1. This will give us a size at the output of 14 by 14 by the number of filters used in this case. I think here the number of filters is 6 because we have number of 6 here, not 16. It may be just 6. Next, we repeat. Yeah, of course. I think we can do the same operation here because the filter kernel size is 5 by 5, start of 1, and the number of filters in this situation, in this at this stage, as here we have a 16 layer. And if you repeat this for the output, you can find that the size is 14 minus 5 plus 2 by 0 over 2 over 1 plus 1. This will give us 10 by 10, and the number of filters will be at this location 16. Finally, we can apply flattening of this data 5 by 5 by 16. If you multiply 5 by 5 by 16, you'll get 400 featured values converted into a tensor or into, let's say, a vector. This vector will be applied to the next stages, which in this case we have, which is the first one is the fully connected layer, FC1. Here the input of the size of the input is 400 with an output size of 120, just one layered fully connected layer. Next step to the next fully connected layer number 2, we have the output of the first one will be applied to the input as an input to the second one, and here we have 120, and the output will be 84 outputs. Now this 84 tensor will be applied to the softmax. The softmax output, the activation function, will be having 10 output classes. Because we have 10 digits, we get at the output 10 different classes according to reading the values from 84 outputs. So you see here that we have reduced the dimension of the tensor or the flattened vector by first time in 2 steps. First time from 400 to 120, second time from 120 to 48, and this is very important not to go in one pass from 400 to 84. This will improve your system. It may be a little bit be time consuming, but it will perform very well and gives you at the output high performance in terms of the accuracy and other evaluation metrics that you are using usually in deep learning. So this is one of the first and very interesting deep learning networks after AlexNet, we call it LuNet, and it was a foundation for the GoogleNet on next stages to build what we call the GoogleNet, and this will be discussed in future lectures, inshallah. This is a detailed overview of the LuNet. As here, this is the same image, and here we have some information about the layers. We have 6 layers. Here we have the feature map size, the feature maps here, and we have the size of the inputs. Here the kernel size, the stride, the activation used in this case the RB tan H, and we used the softmax as a final stage in our system or in this LuNet system. The main idea here is if you look at the total number of trainable parameters in the LuNet 5, you can measure about 60,000 layers or 60K. This can be obtained by having the image size 32 by 32 and getting to the feature maps that are used every time you are taking operations and you try to learn parameters. The outputs are learned parameters if you are applying or modifying their values according to some modification done inside, like convolution, like max pooling, like or other. Usually, the convolution is the main part of applying or main part of that defines the total number of trainable parameters. Nowadays, you may get some systems that have trainable parameters that may approach 12, maybe 20, maybe more mega, or maybe now we're approaching in some systems hundreds of mega trainable parameters in deep learning CNN networks. These links are very useful if you want to go back and see some information about these networks. You can see YouTube channel links, I think I encourage you to have a look on these YouTubes. And for today, that's all talks. I hope that was enjoyable for you. Uh, Please repeat what has been discussed and try to capture the main ideas. And as we said, that the convolutional neural network is a very important part or the building block of the deep neural networks nowadays. And it is consisted of mainly the convolution layer with different types, with max pooling or with pooling layers of different types, maybe, with ReLU activation functions like maybe activation function in general, like ReLU, TAN, H, etc. With also softmax and fully connected layers that are connected usually to perform the task that is required to be utilized or done to get the output in this case. Thank you for listening and I hope to see you very soon. Assalamu alaikum.